We're going to be talking about projectile motion today. This is going to be a relatively involved example. We're going to be looking at question number 1 on the projectile motion worksheet. There's a couple of equations that we're going to need to know to do this to start off with. And we're just going to kind of list the given information out and kind of talk about what's required. Okay, so to start with, you can see here we have an image of kind of what's happening. You have a soccer ball sitting on the ground, and you're going to kick that soccer ball with an initial velocity of 25 meters per second at an angle of 60 degrees. And so the picture looks like this, although the picture is not really necessary, but just to kind of give you an idea. We have two kind of sets of equations that we're going to look at. For the most part, I think the majority of you will probably, if you've done any sort of projectile motion in the past, you've probably talked about an equation that looks like this, where you have 1/2 g times t squared plus the initial velocity times t plus the initial height at the beginning of the situation. And so what you're looking at, we've talked about parametric equations a little bit already. We're setting up two equations. One is going to govern the horizontal changes that the ball goes through, like how far down the line does the ball go based on time. We're also going to be talking about vertical changes. So at any point in time, how high is the ball going? So the ball would be essentially going up to its peak and then back down. So we can look at it in two ways. So this is a way of kind of separating the two things that we can talk about. Well, at a certain time in the example, where does the ball exist? And we can do that with parametric equations independently. So with the other one, if I only looked at the y equation, the one we have originally here, I can talk about time, but it's only going to tell me where the ball is in terms of its height, not in terms of like horizontal distance as well. So let's kind of go through what we would look at here. Originally, if we were to talk about this equation using g, 9.8 meters per second and 32 feet per second are going to make a big difference. And so here you can see g shows up in this equation. You'll have to be careful. Am I using meters? Am I going to be using feet? I believe the example that we're starting off with is in meters per second, just as number 2 is. So you'll do question number 2 essentially the same exact way as I'm going to do number 1. So write these equations down if you want to pause and think about that. Write those things down because we're going to be using these equations as we kind of go through this example. Okay, question number 1 simply says to write a set of parametric equations for the motion of the soccer ball. This is really easy. Basically, you're going to take these two equations here, and you're going to plug in the V0, you're going to plug in the theta, and you're going to plug in the g for both of these equations. And it's something simple where you kind of work it out like this, right? So here you can see the two equations that I've just simply taken. X equals the 25t cosine of 60. And if I work out what cosine of 60 is, that's just 1/2. And so this equation simplifies down to something really nice. It's 25t over 2, which basically says if I want to know where the ball is in a horizontal distance from the beginning to the end of its path, I simply have to type in or multiply time by 25 over 2, and that's going to tell me where it occurs. The vertical distance is a little bit more complicated because we're working against gravity, so we have to add in this gravity constant. You'll see I'm using meters, so I'm using the 9.8 meters per second. So we're going to plug in here. So it's negative 1/2 times g. I'm just going to put the g on the top over 2, so same thing, times t squared. And at this point, a little bit later on, you'll see me kind of take the 25 times square root of 3 over 2, and I'd convert that to a decimal. If you wrote these out as decimals entirely with t and t squared, that's perfectly fine too. It's probably a little bit safer, a little bit easier to deal with later on. Oops, won't do that. So at this point, we're going to kind of look at how we can answer some of these questions. Number 2 says, determine how long the soccer ball was going to be in the air. So this requires me to know a little bit about how parabolas work and what happens. And so what we know is that if I were to hit the ball or kick the ball then that ball is going to take a parabolic path, right? It's going to go up, it's going to hit its peak at some point, and then it's going to drop back down to the ground. And one of the things that we know is that when you kick a ball like this, if you shoot a bullet, if you do any sort of projectile motion, then gravity acts on that object very equally from the start to the finish. So you're going to get a very nice symmetric graph, and it's going to look just like this. So the question is, the ball is going to hit the ground when it hits when the height is at 0, right? So it starts off here at time equals 0, and then at a certain time later on, it's going to hit the ground again. Well, what is the height at these two places? These are the zeros, or the x-intercepts of the equation. And so to find how far it goes, total distance, you're going to take the y equation, and what we want to do is we need to figure out when this happens, right? Question 2 specifically asks, how long is a soccer ball going to be in the air? Well, it's going to take whatever time it takes it to get back down to 0 again. We know I'm going to take the horizontal equation, right? Because we're talking about height. We know that its height would be 0 down here. So we're talking about vertical height. So we're going to set that equal to 0. Now, again, you can see here I've kind of converted it back into decimals. So if you want to do that ahead of time, that might make it a little bit easier. I know that I have a quadratic equation here, and I know that I can factor this thing by factoring out a t in both of these places. So here you see me factor a t out. The good news is that every time you do this kind of situation, it's pretty much going to always be the same. So use this as a pattern when you do the next equation. Factor a t out, and you'll be left with the constant value here times t plus whatever the decimal is here. So it's 21.65 right here. Now, take each one of these and set this piece equal to 0, and then set this piece equal to 0. Now, we already knew at the very beginning of the equation, at time equals 0, we already knew that it was on the ground. So this is not a surprise. This is actually good because it confirms something that I already knew. And so the other part will be obviously the other time it's going to hit the ground. So we're going to go ahead and set this equal to 0 and solve for t. So I'm going to go ahead and add this piece to the other side, and you get 4.9t equals the 21.65. Divide both of these by 4.9, and that should give you the total time that it takes it to hit the ground. And this was 4.42 seconds because it was in meters per second, so that's where you're going to get your time unit from. Okay, and that's probably one of the more complicated process. You got what I just did, even though this is a relatively kind of long question, you've already got the more difficult part down. If that didn't make sense, rewind, watch it again. This is something that you've done plenty of times. It's just factoring. It's just not with a very nice equation. So don't be afraid of the decimals. You're going to get lots of those in real life situations like this. Okay, let's move on to part 3. It's to determine how far the soccer ball traveled in the air. So really what now is, you can see on the graph, I've kind of already labeled it. I need to know what is the total distance away from here? Like, how far did it go? So I want to know what the distance is here. So really, what is this x coordinates? So that's great news because we have an equation that does exactly that. I'd like to know how far did the ball go. So here's something we want to talk about. We know that the ball was in the air, and it would reach its max distance when it comes back to the ground. Right? We're not talking about rolling, so we're not worried about any of that stuff. So I'm going to take that y equation, and I'm just going to basically plug it in. And that's all I have to do here. Super simple part of this one. The horizontal distances are always much nicer to work with because you don't have that extra gravity component. So I knew how long it was in the air. So when it was at this time, I want to know what the distance is. And so we can take the time here, the formula for x distance or horizontal distance, and we can plug in the time that it took it to reach that max distance. And you work that out, and that'll tell you exactly how far it went. Okay, part 4. Okay, this one is easy to find mathematically. Might be a little tricky to explain, but I think you'll get it. If you look at the little picture I drew, we know that the max height will occur halfway through its path. And we know that a parabola's halfway point is called the vertex, right? So if it's halfway from here to here, right, because it's a nice symmetric graph, although my picture is not that great, we know that this would equal, well, half the distance, right? Which means since it's nice and symmetric, it means that the time is also going to be cut in half. And that's something you can kind of bank on. Assuming that it starts on the ground and it ends on the ground, this becomes a very easy thing to worry about. So max height is going to occur at the vertex, and we know that that's going to be halfway through the graph. So take your total time and just cut it in half. There is a different situation where you have, if you start not on the ground, that's going to be a little bit more tricky. There's a nice little formula that we can use, but we'll do that later. Part 5. Okay, so this one requires part 4 to be able to do it. And so we have part 4, it just says determine we're on part 5. Determine the maximum height reached by the soccer ball, and that's pretty easy. If we know when the vertex happens, and that's what we found out in the last one, we know that the max height will occur at 2.21 seconds. The question is, well, how tall is that? Well, you'll take your vertical distance equation, that's the y equation, and you're just going to plug in that time for t. And so you can see me here when I converted that to decimal and plugged it in, and you get about 23.9 meters. So this is max height. Okay. And then the last part would be to graph it. And I'll go ahead and tell you there's really 3 key points that you're going to need to graph, and you already knew one of them. The first one is the origin. In order to do this, we're going to need the vertex, and we need to know where it ends. The good news is you already have this one. You found that at the very beginning. 55.23 was the max distance it reached. And you know that's on the x-axis. You can plot these 2 points here. And then we had found the time, but I didn't know the x-coordinate, like how far. If this is x and y, then how far down the line was it? So I went ahead and pulled up the x formula, the distance for time, for horizontal distance. I plugged in my time for the vertex. It's 2.21, and that tells me the distance away from the origin is 27.6. So down here at 27.6 is going to be your x-coordinate, and we already found the max height, which was 23.9. We found that here. And so go up to 23.9 and create your vertex there, and you can kind of make a nice little curve between those 3 points. And that's basically what you're going to end up doing. This is a pretty long question. It's obviously got 1, 2, 3, 4, 5, 6 parts to it. And so take that. If you need to go back and watch this again or just read through it again, I highly suggest it. Good luck. If you have any questions, let me know. Try number 2, and then we'll definitely hit this first thing tomorrow.